Voyager 1, launched in 1977, is the most distant human-made object in existence. Right now, as you're watching this, it's racing away from Earth at 38,000 miles per hour. That's roughly 11 miles every single second. It has traveled over 15 billion miles from home. To put that in perspective, if you could drive a car at highway speed to Voyager 1, the trip would take you more than 26,000 years. And yet, despite this incomprehensible distance, we can still talk to it. We send it commands. It sends us data back. A conversation across the void. So, how is this even possible? How do we communicate with something so far away that light itself takes over 22 hours to reach it? And perhaps more importantly, how much longer can we keep this conversation going? The answer involves some of the most ingenious engineering ever conceived. A global network of massive antennas and a ticking clock that's counting down to an inevitable silence. Voyager 2 was actually launched first, on August 20th, 1977. Voyager 1 followed 16 days later, lifting off on September 5th, 1977. The names are backwards from the launch order, and that's because Voyager 1 was designed to take a faster, more direct route through the solar system. Both spacecraft are nearly identical twins. Each one is about the size of a small car, weighing roughly 1,800 pounds. Their mission was ambitious beyond anything attempted before. Explore Jupiter and Saturn, study their moons, photograph their atmospheres, and then, if the spacecraft survived, keep going. The problem was speed. Even the most powerful rockets of the 1970s couldn't provide enough velocity to reach the outer planets in a reasonable time frame. So, NASA mission planners came up with something brilliant. They would use the planets themselves as gravitational slingshots. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune aligned in a rare configuration. From Earth's perspective, they formed a cosmic pathway across the solar system. This alignment happens once every 176 years. The next one won't occur until the year 2153. By flying close to each planet, the Voyagers could steal a tiny fraction of that planet's orbital momentum, gaining speed without burning any fuel. It's called a gravity assist, and it's one of the most elegant tricks in spaceflight. Voyager 1 flew past Jupiter in March 1979. The images it sent back were revolutionary. Swirling storms in Jupiter's atmosphere, each one larger than Earth. The Great Red Spot, a hurricane that's been raging for centuries, seen in unprecedented detail. And then Voyager 1 found something nobody expected. Jupiter has rings. Faint, thin rings made of dust particles, invisible from Earth, but undeniable when seen up close. Then it turned its cameras toward Jupiter's moons. On a moon called Io, Voyager discovered active volcanoes, not ancient craters. Active eruptions happening in real time, plumes of sulfur shooting hundreds of miles into space. It was the first time humanity had ever seen volcanism on another world. After Jupiter, Voyager 1 headed toward Saturn. It arrived in November 1980. From close range, it observed Saturn's magnificent rings, revealing that what looks like a few smooth bands from Earth is actually thousands of individual ringlets, each one composed of countless ice particles. Voyager discovered shepherd moons, small satellites, whose gravity shapes and maintains the gaps in Saturn's rings. It also studied Titan, Saturn's largest moon, and found something extraordinary. Titan has an atmosphere, a thick one, composed of about 90% nitrogen, with traces of methane and other organic compounds. In many ways, Titan's atmosphere is more similar to early Earth than any other place we've found. After Saturn, Voyager 1's planetary tour was complete. Its trajectory sent it upward, out of the plane of the solar system, toward the stars. Voyager 2 took a different path. It flew by Jupiter and Saturn as well, but then continued on to Uranus, arriving in 1986, and Neptune, arriving in 1989. These were worlds Voyager 1 never reached. Voyager 2 sent back the first and still only close-up photographs of these ice giants. It discovered new moons, new rings, and revealed atmospheres far more dynamic than anyone had predicted. After their planetary missions ended, both Voyagers kept going. And here's where something counterintuitive happens. Even though Voyager 2 launched first, Voyager 1 is now much farther from Earth. The reason is speed. Voyager 1 is moving at about 10.6 miles per second relative to the Sun. Voyager 2 is traveling at about 9.7 miles per second. The difference is only 0.9 miles per second. That might not sound like much, but imagine you're riding on Voyager 2 and Voyager 1 passes you. In just 1 second, it would pull ahead by 0.9 miles. In 1 minute, it's 54 miles ahead. In 1 hour, over 3,000 miles. After 40 years, that small difference has resulted in Voyager 1 being billions of miles farther from Earth than its twin. Both spacecraft have now crossed a boundary that most people have never heard of. They've exited the heliosphere. Now, the terms solar system and heliosphere have significantly different meanings, and understanding the difference is crucial to understanding where the Voyagers actually are. The heliosphere is a bubble of charged particles blown outward from the Sun. These particles, called the solar wind, stream away from the Sun in all directions at about 1,000,000 miles per hour. They create a protective bubble around our solar system, shielding us from some of the radiation coming from interstellar space. The heliosphere extends far beyond the orbits of the planets, but it does have a limit. At a certain distance, the pressure from interstellar space becomes stronger than the outward push of the solar wind. That boundary is called the heliopause. Voyager 1 crossed the heliopause on August 25, 2012. Voyager 2 crossed it on November 5, 2018. We know the exact moments because the spacecraft carry instruments that measure charged particles. This graph shows actual data from Voyager 1 during the crossing. The lower line shows the number of solar origin particles detected. As Voyager approached the boundary, that number dropped sharply. The upper line shows particles coming from interstellar space. At the moment of crossing, that number spiked. Voyager 1 had left the heliosphere. It was now in interstellar space. But here's the critical part. Leaving the heliosphere does not mean leaving the solar system. The solar system is much, much larger. Far beyond the heliopause lies a region called the Oort cloud, a vast spherical shell of icy bodies surrounding the Sun. The Oort cloud is thought to extend nearly halfway to the nearest star. According to current estimates, it will take Voyager 1 another 300 years just to reach the inner edge of the Oort cloud, and it will take approximately 30,000 years to pass through it completely. Only after that will Voyager 1 truly leave the solar system. So if the Voyagers are so far away, billions of miles into interstellar space, how can we still communicate with them? The answer is a combination of brilliant spacecraft design and massive ground-based infrastructure. Each Voyager carries a high-gain antenna. It's a dish, 12 feet in diameter, and it's the most recognizable feature of the spacecraft. That dish is always pointed toward Earth. The spacecraft uses small thrusters to maintain that orientation constantly. From that antenna, Voyager transmits a radio signal. The power of that signal is just 22 watts. For comparison, that's about the same as a refrigerator light bulb. 22 watts of power, beaming across billions of miles. The signal is incredibly focused. The antenna creates a narrow beam only about half a degree wide. If Voyager's aim were off by even a fraction of a degree, the signal would miss Earth entirely. The signal travels at the speed of light. That's 186,000 miles per second. It's the fastest anything can move through space. And yet, it still takes time to cover the distance. Right now, a signal from Voyager 1 takes about 22 hours and 30 minutes to reach Earth. For comparison, light takes just over 1 second to travel from Earth to the Moon. It takes about 8 minutes to reach the Sun. And it takes roughly 20 minutes to reach Mars when Mars is at its closest. This puts Voyager's distance into perspective. It's not just far, it's beyond far. But distance creates another problem: signal strength. Radio waves follow the inverse square law. This means that when you double the distance, the signal strength drops to 1/4. When you triple the distance, it drops to 1/9. When you increase the distance by a factor of 1 billion, the signal becomes unimaginably faint. By the time Voyager's 22-watt transmission reaches Earth, it has weakened to less than 1/trillionth of a watt. And then another billionth of that. The signal arriving at Earth from Voyager 1 is roughly 1/quintillionth of a watt. To put that in perspective, if you collected all the energy from all the signals ever received from Voyager 1 over the past 40 years, it would barely be enough to power a digital watch for a fraction of a second. So how do we detect something so faint? We use the largest antennas on Earth. NASA operates a network called the Deep Space Network, or DSN. It consists of 3 facilities, strategically placed around the globe. One is in Goldstone, California, in the Mojave Desert. One is in Madrid, Spain. One is in Canberra, Australia. These locations are spaced roughly 120 degrees apart in longitude. This ensures that as the Earth rotates, at least one facility always has a line of sight to any spacecraft in deep space. The network provides 24-hour coverage. Each facility has multiple antennas, but the largest are 230 feet in diameter. That's about 70 meters. These dishes are massive. Standing at the base of one feels like standing next to a skyscraper laid on its side. The surface of the dish is a precise parabolic curve, accurate to within a fraction of an inch. When Voyager's faint signal reaches Earth, these giant dishes collect it, focus it, and feed it into incredibly sensitive receivers. Even with these enormous antennas, the signal is still so weak that detecting it requires some of the most advanced radio technology ever built. But it works. We can hear Voyager. And we can talk back. When NASA sends a command to Voyager, the process is similar in reverse. The Deep Space Network transmits a signal toward the spacecraft. That signal is much more powerful than what Voyager can send. Uplink signals are transmitted at 20,000 watts. But even with that much power, the signal still takes over 22 hours to reach Voyager 1. So if engineers on Earth want to send a command and get confirmation that it worked, they have to wait at least 45 hours. 22 hours for the command to arrive. Time for Voyager to execute the command. Then 22 hours for the confirmation signal to return. Communication with Voyager isn't a conversation. It's more like sending letters across an ocean. You send something, and then you wait. Days pass before you know if it was received. But this slow exchange of signals is still enough to operate the spacecraft and receive scientific data. And that brings us to another problem: power. Transmitting signals requires energy. Running instruments requires energy. Keeping the spacecraft warm in the freezing void of space requires energy. Voyager can't use solar panels. At its current distance, the Sun is too dim. Sunlight at Voyager 1's location is about 3,600 times fainter than it is on Earth. Solar panels would be useless. Instead, Voyager uses nuclear power. Each spacecraft carries 3 radioisotope thermoelectric generators, or RTGs. These devices contain pellets of plutonium-238. As the plutonium decays, it produces heat. That heat is converted into electricity using thermocouples. It's the same technology used on other deep space missions, including the Mars rovers Curiosity and Perseverance. At launch, each Voyager's RTGs produced about 470 watts of electrical power. That's enough to run several household appliances. But plutonium-238 has a half-life of 87.7 years. This means that every 87.7 years, the power output drops by half. After more than 45 years of flight, Voyager's RTGs are now producing less than 220 watts. And the power continues to decline. About 4 watts are lost every year. To conserve energy, NASA has been shutting down non-essential systems one by one. In 1990, after Voyager 1 completed its flyby of Saturn and began its journey out of the solar system, NASA made a difficult decision. They commanded Voyager 1 to take one last photograph. The target was Earth. From a distance of nearly 4 billion miles, Voyager turned its camera back toward home. In the image, Earth appears as a tiny speck, a pale blue dot, barely a single pixel, suspended in a beam of scattered sunlight. Carl Sagan, one of the scientists involved in the Voyager mission, later wrote about that image. He described Earth as a mote of dust, floating in a sunbeam. Every human being who has ever lived on that dot. It was the last picture Voyager 1 ever took. After that photograph, the camera was shut down permanently to save power. It has never been turned on again. Voyager 1 launched with 10 scientific instruments. Most of them are now off. Only 4 are still active. The magnetometer, which measures magnetic fields. The plasma science instrument. The low-energy charged particle detector. And the cosmic ray detector. These instruments continue to study the environment of interstellar space, sending data back to Earth. But even these will eventually have to be shut down. NASA carefully plans each shutdown, trying to extend the mission as long as possible. The agency estimates that by around 2025, they'll have to turn off another instrument, then another a few years later. By the early 2030s, there may not be enough power to run any instruments at all. Even after all the science instruments are off, Voyager will still be able to transmit basic engineering data, its location, its orientation, the status of its systems. But eventually, there won't be enough power even for that. The signal will stop, and Voyager will go silent. Despite declining power, both Voyagers have faced technical challenges over the years, and engineers on Earth have had to solve problems across billions of miles of empty space. In 2023, Voyager 2 experienced a communication crisis. During a routine sequence of commands, the spacecraft's antenna shifted by just 2 degrees. That may not sound like much, but at a distance of billions of miles, a 2-degree error is catastrophic. The narrow beam of Voyager's transmission no longer pointed at Earth. Communication was lost. NASA couldn't send commands. They couldn't receive data. For all practical purposes, Voyager 2 was gone. But the engineers who designed Voyager had anticipated this exact scenario. Decades earlier, they had programmed the spacecraft with an autonomous safety feature. Several times each year, Voyager automatically checks its own orientation. If it detects that the antenna has drifted, it corrects itself. So even though NASA couldn't communicate with Voyager 2, they knew the spacecraft would eventually fix the problem on its own. They just had to wait. Weeks later, right on schedule, Voyager 2 reoriented itself. The signal returned. Communication was restored. Voyager 1 has had its own problems. In 2023, the spacecraft began sending garbled data. The information made no sense. It looked like random noise. Engineers spent months diagnosing the issue. The problem, they eventually discovered, was a corrupted memory chip in one of Voyager's 3 onboard computers. The computer was trying to package science data for transmission, but the corrupted chip was scrambling the information. NASA sent new instructions, telling Voyager to route the data through a different part of its memory. The fix worked. The garbled data stopped. Clear signals resumed. NASA is also preparing for future problems. One concern is the thrusters. Voyager uses small thrusters to keep its antenna pointed at Earth. These thrusters fire in tiny pulses, just milliseconds at a time. Over the decades, residue from the thruster fuel has been building up inside the fuel lines. Eventually, this residue could clog the system, making the thrusters unreliable. To extend their life, NASA reprogrammed the thruster software. Instead of firing in many short bursts, the thrusters now fire in fewer, longer bursts. This reduces the number of times the valves open and close, which slows down the rate of clogging. The change is expected to extend the life of the thrusters by about 5 years. Every solution buys a little more time, but time is running out. As the Voyagers move farther from Earth, the signal strength continues to decline. The Deep Space Network antennas can still detect the transmissions, but the margin for error is shrinking. NASA expects that by around 2036, the signal will become too faint to detect reliably. That means we have, at most, about 12 years left. 12 years to continue this conversation. 12 years before the silence. Voyager 1 and Voyager 2 were launched in 1977. Their primary mission was supposed to last just 5 years. Fly by Jupiter and Saturn. Send back some pictures. Then the mission would end. Instead, they've been operating for more than 46 years, nearly 10 times longer than planned. They've left the heliosphere. They're traveling through interstellar space, and they're still talking to us. The computers on board the Voyagers have less memory than a modern car key fob. Their data storage is about 13 millionths the capacity of a smartphone. Their communication speed is roughly 138,000 times slower than a standard home internet connection. By today's standards, the technology is ancient. And yet, these machines have traveled farther than anything humanity has ever built. They represent the absolute frontier of exploration. Right now, Voyager 1 is moving through a region of space no human-made object has ever reached. It's detecting cosmic rays that have traveled across the galaxy for millions of years. It's measuring magnetic fields that exist between the stars. It's sending us data from the edge of everything we know. And it's doing all of this with a 22-watt transmitter and a set of antennas on Earth that can hear a whisper across the void. The engineering required to maintain this connection is staggering. Every signal sent, every command received, every byte of data transmitted across 15 billion miles. It's a testament to human ingenuity, but it's also a reminder of our limits. We can build machines that travel to the stars, but we can't make them last forever. The plutonium decays, the power fades, the thrusters clog, the signal weakens. One day, possibly in 2036, possibly a few years earlier, possibly a few years later, the Deep Space Network will listen for Voyager's signal and hear nothing. Engineers will try again the next day, and the next, but the silence will continue. Voyager 1 will still be out there, still traveling, still moving at 38,000 miles per hour through the darkness. But we won't be able to hear it anymore, and it won't be able to hear us. The conversation will be over. After that, Voyager will drift. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. It won't stop. It won't slow down. It will simply pass by, a silent emissary from a distant world. If the golden record attached to its side is ever found, if some other intelligence ever discovers it floating in the void, they'll find sounds and images from Earth. Music. Greetings in 55 languages. Pictures of humans and animals and cities. Instructions on how to play the record, etched onto its surface. A message in a bottle, cast into an ocean larger than we can comprehend. But for now, Voyager is still ours. We can still hear its voice, faint, fragile, traveling across a gulf of space so vast that light takes nearly a full day to cross it. And every time we receive a signal, every time those massive antennas in California and Spain and Australia lock onto that impossibly faint transmission, we're doing something extraordinary. We're listening to the most distant whisper in human history. A machine we built nearly 50 years ago, telling us what it sees at the edge of forever.